So in today's video, we'll be differentiating rational and irrational numbers. Basically determining if a number is rational and irrational. How do you do the steps for that? So a rational number is going to be a number where you can write it as an integer divided by an integer. And an integer being a whole number like -6, 1, 0, 5, those kinds of numbers. So two properties about decimal places about rational numbers is it's either going to be repeating, so where it's going to have a pattern with the decimal places, or it's going to be terminating, which means that it stops at a certain point. Now, your irrational numbers are going to not fit any of these terms. Irrational numbers, you're not going to be able to write it as an integer over integer. It's not going to have repeating decimal places, and it's not going to be terminating. All right, so let's try a number like the square root of 25. The square root of 25 is going to give you 5. Now, let's see if we can try to write 5 as an integer divided by an integer. Well, we know that 5 divided by 1 is going to give us 5, and 5 and 1 are integers. So therefore, 5, or square root of 25, is a rational number. Now, is it repeating or is it terminating? Well, 5 stops at 5. It doesn't have any more decimal places. It doesn't repeat. So therefore, it's going to be terminating decimal places. So that's going to be your answer. All right, let's try a number like 33 divided by 9. Well, 33 divided by 9 is already in that integer over integer form. 33 is an integer, 9 is an integer. So therefore, it's going to be rational. Now, is it repeating or terminating? Well, if you break down the fraction a little more, we can pull out a 3. We can do 11 times 3 is going to give us 33. Divided by 3 times 3 is going to give us 9. When we set it up this way, we can cancel out those 3's. So then our final fraction is going to be 11 over 3. Whenever you put 11 over 3 in your calculator, you're going to get 3.6. And the 6's go on forever. And it's going to repeat this pattern of 6's. So therefore, the decimal place behavior is going to be repeating. So it's going to be rational and repeating. Now, what about the square root of 11? Well, the square root of 11 you can't write as an integer over an integer, because square root of 11 is not an integer. So therefore, we know that the square root of 11 is going to be irrational. Now, we have to make sure that the square root of 11 is not repeating and terminating, just to be sure. We've already determined it's irrational, so it can't be repeating or terminating, but just to check, let's see. So the square root of 11 is going to give you 3.31662479, and it's going to go on. It's going to be way more digits. So it's not repeating, so that's good, and then it's not going to terminate. Whenever you have a non-perfect square root, like the square root of 11, the square root of 12, 13, as long as you don't get a whole number out of it, it's going to go on forever. So therefore, the behavior behind the decimal places is going to be infinite. So that's your answer. Now let's try a number like 17 divided by 34. 17 divided by 34 is already in that form of integer over integer. We can also simplify 17 divided by 34 as 1 divided by 2. So we know that 1/2 is a rational number. One is one is an integer, 2 is an integer, and it's in that form, so we know it's rational. So now we just determine if it's repeating or terminating. Well, 1/2 is, if you put it in your calculator, it's going to give you 0.5. 0.5 ends at this 5. So therefore, the behavior is going to be terminating. Now for this last one, we're going to do 0.03303330333, and so on. So for this number, can we write it as an integer divided by an integer? Well, you can't, because 0.30 and so on is not an integer itself. You can't do that number divided by 1 because 0.303 and so on is not an integer. So therefore, it's going to be irrational. And then, since it's irrational, the decimals are going to go on forever. Now, it may look like it's repeating, but notice that it's 303, 303, and then we get to 33, so it messes up the pattern. So it's not repeating, and it's not going to terminate because of these dots right here. It's going to go on forever. So the decimal place behavior is going to be infinite. So that's your answer. Now, what about -10/3? Is this rational or irrational? And what is the decimal place behavior? Well, -10/3 is going to simplify out to 3.3 repeating. Or it's supposed to be negative, sorry. -3.3 repeating. So, since it's already written in integer form, it's going to be rational. And the decimal place behavior is going to be repeating, because that 3 is going to repeat and go on forever. So that's the decimal place behavior, and if it's rational or irrational. Now, what about the square root of 5? If you recall back, I said anytime you have a non-perfect square root, where you put you would plug it in your calculator and you would get a non-whole number, then it means that that square root is irrational. So if you get like the square root of 4, you know that's 2, that's a whole number. But if something like the square root of 5 or the square root of 3, you're not going to get a whole number. So let me plug in the square root of 5 in my calculator. I get 2.236067977. You can't write the square root of 7 as an integer over an integer. So therefore, it's going to make it irrational. And the decimal place behavior for all irrational numbers is going to be infinite. So that's going to be your answer. Now, what about negative times square root of 287? Now, the square root of 287 is going to give you 17. So it's going to be negative times square root of 289, which is 17. So it's a negative times 17, which is just going to give you negative 17. You know that negative 17 you can write as an integer over another integer. We can do negative 17 divided by 1. We can do negative 34 divided by 2, and so on. So it is rational. We can write it as that integer over integer form. Now we need to determine the decimal place behavior. Negative 17 ends at the 17. There's no more decimal places that continue. So therefore, it's going to be terminating decimal places. Now, what about something like negative 6 pi? Pi is going to be irrational. Let me give the digits for it. Pi is going to be 3.141592654. And anytime you have an irrational number times a rational number, it's always going to give you a irrational number. So it's going to be negative 6, which is rational, times pi, which is irrational. If you plug negative 6 pi in your calculator, you're going to get an infinite value. So, but I get 18.8495592 and so on. So this is going to go on forever. So you know that this is irrational because you can't write negative 18.8 and so on. You can't write that as an integer over integer. So it's going to be irrational, and the decimal place is going to be infinite. So that's your answer. Now, what about a number like 0.61538461538 and so on? Can you identify a pattern? Well, if we look, we have 615384 and we have 615384. So there is a pattern, and then there's going to be a 6 1 again, and it's going to repeat and so on. So the pattern repeated twice, and it would continue repeating if the values were shown. So since it's repeating, we know that it's rational. And the decimal place behavior is going to be repeating. So that's your answer.